All right, y'all. So we got two more easy topics to cover here in order to button up chapter 16. Okay. These aren't too bad, I promise. The first one is what's called a reaction quotient. Okay. And we're going to use the variable Q for this. I think it's going to be easiest to explain this in a context of an actual chemical reaction. So let's just take a look at an example here. Nitrogen gas, and I'll balance it for the sake of time, plus hydrogen gas. 3 equivalents will produce 2 equivalents of ammonia gas. All right. And so what we had learned is how to construct our equilibrium expression given our balanced chemical equation. Right. So in this case, I'll do it in terms of pressure. You could, of course, do it in terms of concentration. So Kp is the products over reactants, so the pressure of the ammonia squared divided by the pressure of the nitrogen gas times the pressure of the hydrogen gas cubed. Okay, and we call it K when the pressures are at equilibrium. Right, so if I tell you at equilibrium, the pressure of the, let me get my calculations here. The pressure of the nitrogen gas is equal to the pressure of the hydrogen gas at 1.25 atm. And the pressure of the ammonia is 2.75 atm. Right? If I tell you that we're at equilibrium, it's really easy to find the value for that Kp. You're just going to plug in those values into our expression. So Kp equals then these equilibrium values, so the 2.75 squared divided by 1.25 times 1.25 cubed. Punch that into my calculator, and I get 3.098. Okay. So that's all well and good when I tell you that it's at equilibrium. Okay. Q, the reaction quotient, is when we evaluate our equilibrium expression using any values other than the equilibrium values, right? So when we take this same expression here, but we don't know what the equilibrium values are, all we know are just random sort of initial concentrations. If we plug those into that same equation, instead of calling it K, or equilibrium constant, we call it Q, right? So evaluate our equilibrium constant at any conditions other than equilibrium. Okay, so let's take this same example. I told you what the equilibrium values are for these pressures, and thus we could figure out what Kp was. All right, but now let's say, now we're going to just pick random initial values for all of these pressures, right? So we're going to say that the pressure of the nitrogen gas, so let's say if the pressure of the nitrogen gas is equal to, let's say, 3.5 atm, the pressure of the hydrogen gas is equal to 0.75 atm. It's kind of messy. And the pressure of the ammonia gas is at 1.25 atm. Okay. And we can ask, which direction will the reaction proceed? right? If it were outside of equilibrium, then it's either going to be shifting towards the products in order to reach equilibrium or towards the reactants in order to reach equilibrium, right? When we're at equilibrium, of course, these pressures don't change. They're constant. That's how we can calculate this constant value here. But at any point other than equilibrium, these pressures are going to change until it reaches equilibrium. Okay, so this is where Q becomes very useful. I can calculate Q by, again, just using this exact same expression here, but plugging in values other than our equilibrium values, right? So now I'm going to plug in my 1.25 squared over 3.5 times 0.75 cubed. Okay. And this would give me a reaction quotient of 1.058. All right, let me make some room here. So why is this useful? Because we can just take this value of Q and compare it to our value of K. And there's this very simple relationship that will tell you which direction this reaction is going to proceed. Okay, so if Q is equal to K, then we're at equilibrium. Nothing's going to change, right? But if Q is less than K, this reaction will move in the direction of the products, in the forward directions. So progress towards the products. Okay, and then if Q is greater than K, the reaction will proceed in the reverse direction. So it will progress towards our reactants. Oops, reactants. Okay, so by evaluating our Q here and comparing it to our value of K, we can see that Q is less than K, and thus under these conditions, these starting conditions here, our reaction will progress towards the product side, right? So our reactant concentrations, or in this case, pressures, will decrease, and our product pressure will increase. Okay, so that's why we care about a reaction quotient. If we know the KEQ, then we can just take any old starting conditions, plug them into that expression, and compare the value of Q, our reaction quotient, to that equilibrium constant to tell which direction the reaction is going to progress. All right, and this is related to a similar concept. Last one we're going to talk about here, which is called Le Chatelier's principle. All right. And Le Chatelier's principle basically simply says that a change in any one of those variables in our equilibrium expression is going to produce a shift in the other variables that will counteract the effect of that change. Okay, so what do I mean by that? So let's just take our same sample reaction here. Oops, gotta balance. Okay, so let's say that we have this system here at equilibrium, and then I decide I'm going to increase the concentration of nitrogen, or the pressure of the nitrogen gas. Okay. If I increase the pressure of the nitrogen gas, now all of a sudden I've thrown the system out of equilibrium, right? Because it was previously in equilibrium. So the system's going to compensate in order to get things back to equilibrium. An increase in the concentration of this reactant here will lead to a decrease in my other reactant. Okay, basically it's going to start shifting the reaction towards the product side, right? So let's actually say that first. So increase in nitrogen will end up shifting this reaction to the right, which means a decrease in the concentration of hydrogen gas and an increase in the concentration of ammonia. Okay, so now let's think, if instead of increasing nitrogen, what would happen if all of a sudden I took away a bunch of nitrogen, right? I let this system go to equilibrium and then I remove some of the nitrogen. So we're going to decrease the concentration of N2. This is going to have the reverse effect, where now we're going to shift things to the left. Which means that we're going to decrease the concentration of ammonia and increase concentration of H2. All right, so then let's just take a look at another sample reaction here. So let's do CH4. Okay, so what happens if I increase the concentration of O2? Okay, so what we want to be able to answer is, if I increase the concentration of O2, which direction does it shift towards? And then what happens to the concentration of everything else, right? So all of these other things here. What's going to happen? If I increase one of my reactant concentrations, that's going to shift everything over to the right, which means that my product will increase in concentration and my other reactant will decrease in concentration. Right? In order to get back to equilibrium, everything's going to have to adjust itself to that increase in oxygen. And so this is how the rest of the system will compensate. Okay. What about, let's just clear all this off. Let's say that I decrease the concentration of CO2. All right, so this goes down. How will that shift things in this system? So I guess I got to replace this with my other reactant here. If I decrease the concentration of my product, it has the same effect of increasing the concentration of my reactant. That also is going to cause the system to shift to the right, meaning that my reactant concentrations will decrease and the water concentration will increase. One more just for the sake of completeness. let's say that I decrease the CH4 concentration. Okay, see if you can't fill in here what will happen to the rest of the system. Which direction will it shift? Start there. I think that that's the easiest way to think about it. Because once you know which direction it's going to shift, it's easier to figure out what happens to all the other compounds, all the other concentrations. Right? So if this goes down, the system is going to have to respond by shifting to the left. Right? A left shift means an increase in the concentration of oxygen and a decrease in the concentration of my two products. All right, and these two are very closely related concepts, the reaction quotient and Le Chatelier's principle. The reaction quotient is just sort of a quantitative way of thinking about Le Chatelier's principle, where Le Chatelier's principle is just sort of like a more qualitative way of thinking, okay, I decrease this, how do things shift? If ever in question, you can plug in numbers and convince yourself that that is indeed going to be the effect, right? You can sort of make up a value for K and then increase one of those values and see that your Q is going to be, either less than or greater than K, and that will tell you which direction it shifts.